Okay, so this is my recap of VSEPR theory of molecular geometry. And VSEPR is just an acronym for valence shell electron pair repulsion, which is just a big complicated way of saying that electrons want to repel each other. And specifically, it's the valence shell electrons, the ones that are part of bonding and forming these molecules that we've been drawing. And so those special electrons repel each other just like normal electrons. So in a molecule, those electron groups, those electron pairs, are going to want to be as far away from each other as possible. And that's the entire idea behind this VSEPR theory and all these geometry terms we're going to be using. So that's what it's based on. And we actually have two different geometries. Electron pair geometry is when we can see all of the electrons in a molecule, the bonds and the lone pairs. Now, we can't actually see those lone pairs in real life, so we have that molecular geometry where we only see the bonds and we only name the shapes that's formed by the bonds in our molecule. So, those are our two different geometries, and we're first going to focus on the electron geometry. They're a little bit simpler to understand, and we're going to base everything else on these. Now, quick little side note. Anytime you see two atoms, like just two atoms, both of their geometries is going to be linear diatomic, because you simply have two atoms, and 2 points make a line. There's no other shape that can be made by 2 points. So, anytime you see two atoms, it's linear diatomic. We are about to look at the example of things that are just plain old linear. And those are linear, they do form a line, just like our linear diatomic, but that's because I have two groups around one central atom. So those two groups around the outside are both bonded to the central atom, but they're trying to stay as far apart from each other as possible. So they make a line. And we can actually see that happen in this simulation that I have. If we add two bonds, it works for any kind of groups around that central atom. I try and tug them closer, they're going to be repelling each other and spreading out as far as they can from each other. And the simulation also shows us that's going to be a perfect 180 degrees apart, as far apart as they can be from each other. So this is linear because it's a line, but it's not linear diatomic because it's made of more than just two atoms. So our next geometry is trigonal planar. When I have three groups around the central atom, it makes a triangle. And trigonal is just our kind of complicated way of saying triangle. But then we add in that word planar because this molecule is going to be have all of its bonds, all of its atoms, all in the same plane. There's this nice straight line all the way through all of them. So this is a flat triangle or trigonal planar. And then four groups is called tetrahedral. You might think that four groups would make a square or a rectangle, especially since we've been drawing out things like CH4, like this. On paper, it is going to look like a square, and we do draw a lot of our molecules at right angles because remember, we're trying to fill up all four sides of this kind of invisible box around carbon, trying to get it full and happy with its 8 electrons. But in real life, these molecules can move around in 3 dimensions. And so right now, these hydrogens are only 90 degrees apart in 3 dimensions when we give them more space to be in this tetrahedral shape. And we've already used the word tetra to mean 4 already. But in this tetrahedral shape, each of those atoms has 109.5 degrees. That's almost 20 degrees more space if they expand and move into this tetrahedral shape instead of staying in that flat square space. They really do not want to be any closer together than they have to be. So those are our basic electron geometries. Now, each of these molecule geometries we're going to talk about is kind of being specific about what those groups are. Electron geometry, it didn't matter whether it was bonds or lone pairs making these shapes. But now we're going to be specific. If in that two-pair example, those two different groups are both bonds, then in our molecule geometry, we can see everything. And so that is still going to be called linear molecule, just like the electron pair geometry. If in our three-pair example that we looked at before, if all three of those are bonds and none of them are lone pairs, then notice our molecular geometry is the exact same as our electron geometry was, because there's no lone pairs. So without the lone pairs, we're just seeing bonds, just like in a molecular geometry. Now, if only two of those three groups are bonds and one of them is a lone pair, then I'm only seeing two things, and those two bonded atoms. So your geometry teacher would say, oh, 2 points, that makes a line. But even though we're only seeing two things, this one lone pair here is still going to have an effect on the molecule. It's still there, pushing against the rest of those electrons. And so this isn't going to be a straight line. This line is going to get a little bit bent. And that's what we call the geometry. The molecule geometry, when you have two bonds and one lone pair, is bent. And we can see this happen in our simulation. Here we have those two bonded atoms, and when I add a lone pair, they have to scooch a little bit closer together because this lone pair still repels them. It still takes up space. So, no lone pair, lone pair. They squish a little bit closer together just by adding that. But if we don't see that lone pair, then all we're seeing is this bent molecule. But if I do see that lone pair, then I can see the triangle, and it is a flat triangle, because even though that is a lone pair, it's still in the same plane as everything else that we have here. So, switching back. Now, let's imagine that we have our tetrahedral electron geometry. If all four of those groups are bonded, no lone pairs, we have a tetrahedral molecular geometry as well. What I say, in general, kind of rule of thumb, if there are no lone pairs, then there's no difference between our names. Now, if one of those groups is a lone pair, so if I have three bonded atoms with one lone pair on it, when I'm thinking about my molecular geometry and I can only see the bonds, I can only see three things. So my brain should start thinking, oh, that's going to be like trigonal something, just like the other trigonal that we've seen. And that is true. But this time, this is going to be trigonal pyramidal, because just like that line, I have a lone pair here on my triangle. And even though I can't see it in my molecular geometry, it has an effect on those three bonds, and it pushes them closer together. So we can see that in our simulation. If I get rid of this lone pair for a second, and I've got my three bonds, then I add my lone pair. It squishes them closer together. Ooh, don't want to go there. So that trigonal pyramidal is because now these are just a little bit more squished together into a little bit of a pyramid there. And then last but not least, if I have two bonded atoms and two lone pairs, in total I have four groups around my central atom. So the electron geometry is tetrahedral, but the molecule geometry, and I can only see bonds, so I'm still only seeing two things, but I've got two lone pairs on that two things, then that's going to be bent. Because start thinking it's a line because there's two atoms, two bonds there, but it's not going to be a straight line. It's going to be a bent line, just like when I had my bent earlier, except this time I have two lone pairs on that line, so this is going to be a little bit more bent than it was even before. So we have bent here, and we have extra bent here. But tetrahedral in its electron geometry, if I can see all four of these things, then it's going to look like a tetrahedron. But if those electron groups, those electron pairs that aren't bonds disappear, then I just have a bent atom again. So that's all the special names that you need to know. Now, I'm going to go through a few problems on pages 5 and 6 to help us go through the process of uncovering these names from the actual Lewis dot structures. So the first molecule that we have to look at is hydrofluoric acid, HF. And even though I'm going to show you another process, as soon as I see this, I don't really like this being the first example, but I guess we get it out of the way. I see 2 atoms. This is a molecule made entirely of just 2 atoms, so I'm not going to bother counting bonds and lone pairs and stuff. My answer is linear diatomic for both of these names. Now, if we take a quick second to look the rest of the way down the page, do you notice any other molecules that are going to be linear diatomic? Even if you haven't drawn the structure out, hopefully you're noticing N2. 2 atoms, has to be linear diatomic. That's it. So, now, if we do look at something like H2O, I've got 3 atoms here. The only one that really matters for this is the central atom, and how many things are around that central atom. So, O is our central atom here, and it has 2 bonds, one on either side, and 2 lone pairs. It doesn't matter how many individual dots it is, it's how many pairs of dots we have around the central atom. So, if I'm thinking about my electron geometry here, I can see all of the electrons in our molecule. That means bonds and lone pairs. So that's 2 bonds, 2 lone pairs. All together, that gives me 4 things. That means that my electron geometry is going to be tetrahedral. Remember though, the molecular geometry, we only see the bonds. So I'm looking and I have 2 bonds. My brain should be thinking, 2 makes a line. But I always need to check anytime you think something's linear, does it have lone pairs on that line? And in this case it does, so that's not going to be a straight line, that's going to be bent. So that's the way we're going to analyze this, is look at the molecule, count up these numbers, probably never going to ask you for those numbers again, but you use them to find those names. So, CH4, 4 bonds around that central atom, no lone pairs, no dots to be seen. So, in my electron geometry, bonds plus lone pairs, 4, that's going to be tetrahedral. In my molecular geometry, I can only see my bonds, but I had 4 bonds, so that means this is also tetrahedral. Now, CCl4 is a little bit more complicated, but I still see those 4 bonds there. And you might think that this has 12 lone pairs, which technically it does, but none of those lone pairs count because they're not on the central atom. They don't affect the shape unless they're on the central atom. So these numbers look awfully similar to CH4, and our names are going to be exactly the same as well. In our next molecule, NH3, we have 3 bonds around that nitrogen and 1 lone pair. In my electron geometry, when I can see all of those things and there's no difference, means I'm seeing 4 things. Big surprise, this is tetrahedral again, but this molecular geometry is not going to be tetrahedral. In this molecule, I only see the bonds, so I only see the 3 things there. So this is going to be trigonal something. And I just have to figure out, is that going to be trigonal planar or trigonal pyramidal? And in this case, it's going to be trigonal pyramidal because we have this lone pair on that triangle. It's invisible in our molecular geometry, but it still has that effect of bending our bonds a little closer together into that pyramid shape. Now, CO2. If you're thinking that this has 4 bonds, I can kind of see what you're thinking because there are 4 lines there. But this right here, if I asked you, hey, what's this? You'd probably tell me, oh, it's a double bond. And your words there, it's a double bond. That's 1 bond. So carbon has 1 bond over here and 1 bond over here. That gives it a total of 2 bonds. Now, they are twice as strong with twice as many electrons, and we talked about how they're going to be shorter than a single bond, longer than a triple bond. There's also different properties of these double bonds, but it's still one bond. Now, no lone pairs, because they're not on my central atom, they don't count. Electron geometry, I see two things, so I'm thinking it's a line, and this time it is going to be linear, and it's not going to be bent because there's no lone pairs to bend my line. In my molecule geometry, when I only see bonds, I see two bonds. That makes me think linear, and that it is. Now, BF3, I have 3 bonds, no lone pairs because they're not on my central atom, they don't count. So 3 things makes me think trigonal, and this time it's going to be trigonal planar because there's no lone pairs. And then molecular is also trigonal planar, no lone pairs, no difference in my names. Now, I know I saw some people in class that had drawn BF3 a little bit differently. They'd taken an electron group from here and turned it into a double bond here. And even if you had made that mistake and you had forgotten that boron is happy with 6 electrons around it, it doesn't need 8 like all the other atoms. When we're looking at this new molecule that you've drawn that doesn't have these electron stuff up here, notice boron still has 3 bonds, no lone pairs. So even if you make a little mistake in your structure, that doesn't mean that you're going to mess up your names. So work on these names, get them down, get the way to classify them down, and you're going to be great. So I'm actually going to leave page 6 for you to practice doing the same thing, just going through the electron and molecular geometry. Don't worry about polarity or IMF. The one that I am going to do with you real quick, though, is methanol, because it's a little bit weird. But remember, I've told you before, carbon loves to be the central atom. Like, if it's not the central atom, it's going to kill whatever atom that is and become the central atom. So carbon is our central atom here, and you can see that it just has 4 bonds, no lone pairs. And we've seen several different examples like this where it's just going to end up being tetrahedral. Now, this OH group, this hydroxide group that's sticking off over here, is going to mean that one of those lobes of the tetrahedron is going to be a little bit bigger than the others. It's going to kind of look like this squid shape here. It's just going to have a little bit more because it has the O and the H, but it's still going to be that same basic tetrahedral. So, finish up the rest of these examples and those molecules on page 6, and be ready to go over polarity and IMF in class.